Yeah, so I'm Andrea Piseri. I study at Università degli Studi di Milano, and I would like to talk to you about my process of learning APL by joining the student competition. So, as said, I'm a math student as well, so it seems that there's quite a few of us today. I mainly enjoy abstract algebra and mathematical logic, but recently I've taken an interest in computability theory, and so that brings me quite naturally to programming. In fact, as a hobby, I've been writing some software kind of for fun. I learned quite early some little bits of Python, but I never took it very far. And I picked the hobby back up in university, actually, because I had to take a C programming course, and yeah, I kind of stuck with that for a while. But then a couple of years ago, I picked up the habit of learning programming languages. So I did a bit of C and C++, which was what I already knew a little bit about. But then I started with Rust, learned a little bit of Haskell, and then ultimately I got to APL and BQN as well. So my journey started, as I said, a couple years ago, and the first ever array language that I used was MATLAB. So we can all take a moment to appreciate the fact that MATLAB is actually an array programming language, even though it doesn't look like it. There are quite a few things that I didn't like at the time about MATLAB, which APL actually shares. So it is an interpreted language, it is dynamically typed, it has kind of a weird syntax compared to C. And so I didn't enjoy programming in MATLAB at the time, and I still don't, but APL kind of changed my perspective on some of these topics. So for the time being, I went back to C, and then I had a little bit of experimentation with competitive programming, and I noticed something that, which is that in competitive programming, it is very common to use just a simple array as a data structure. Right, so the only time when you reach for something else is it's either a tree or a hash map. But arrays completely sweep the competition in competitive programming. And so I thought, yeah, maybe there's something there, but for the time being, I had a little bit more fun, so I learned a little bit of Haskell from Zoding's community, who is a YouTuber who does something that he calls recreational programming, and I started doing that as well, which is exploring wildly random ideas. And about MATLAB, I really like the information density and the mathematical style of definitions, which was completely missing in C. And then, so when last year I first encountered APL, it was with Connor Hoekstra's YouTube channel again. And these qualities that Haskell had struck me with were even more pronounced in APL. So instantly I fell in love. And the first thing I did was that I joined the competition, I joined the challenge of Advent of Code in December 2022, and I used that to learn the language. So I solved a few problems, so I encountered a new difficulty every day, which pushed me to learn the primitives kind of one at a time instead of sitting down and studying all of them, which would have been, I think, the completely wrong way to approach learning a new language. And I have some solutions to that on GitHub, and I think I'm quite happy about is that almost all of the solutions that I found were actually short enough to fit in a Mastodon tooth, so they were less than 500 characters. And I finished days 1 to 20 with a couple holes. And after that, I gave MATLAB a new chance. So I had a programming project in university, which was in image processing. And I tried applying some of the things that I learned with APL to those problems. And I found out that I could get quite a bit more performance out of MATLAB by just avoiding the iteration and loops that I was taught in the MATLAB course in university, and just trying to get the most out of structures like outer product and such, which are available in MATLAB even if they're quite limited. So this brings us to the competition, which I joined slightly after. And I'm going to present two tasks today, which are both from part 2. We have in task 5 the implementation of reading frame translation in bioinformatics. And I particularly liked this problem because it's an example of something that you might encounter in the real world, right? It's kind of problem that you might actually want to solve. And I also gave two very different solutions to this problem. The first one I'm sure I submitted, and it was the first one that I found. But then later I found a different one, which, and this is kind of embarrassing, I'm not sure if I actually ended up submitting the second solution, so I'm going to present them both, just because I think that the difference in the kind of implementation that I gave is quite interesting. But again, I'm not sure which one was actually the one that got evaluated. So, and for part 2, I chose to present task 3, which was the coins problem, time for a change, which I really enjoyed, mainly because as a mathematician, I always appreciate a good opportunity to use induction. And also there's some improvement that we may be able to make to my solution if there's some time left over. So let's get on with problem 1, which was reading frame translation. First, we will need to write a function that, given the name of a file in FASTA format, will return the protein strings. So just to be familiar with it, a FASTA file looks a little bit like this. There is a header that starts with a greater than sign, and then the following lines encode a DNA sequence. And the output that we want from this function will be a list of all of the possible proteins that we may encode from this DNA in either of the 6 possible reading frames. So, as you may know, the DNA can be read in triplets that are called codons, and you may start reading at any offset between 1 and 3. And you may also start reading the complement string to the one that is encoded, in which case you start reading from the end, and you apply the complement of the bases. So the output might look like something like we have below, which is a list of protein sequences. Right, so the final structure of the solution will look a little bit like this. I will not investigate the implementation of the functions AAS and read FASTA, because it's a bit outside of the scope of what I want to show right now. But read FASTA basically just opens the file, gets out the sequence, and spits out a string of DNA. We have this little disclose of the reverse of the disclose, which discards the header from the output of read FASTA and just gives the sequence. And then the AAS function will simply take the DNA sequence and return the lists of amino acids that we can read sequentially from start to end in either of the 6 reading frames. So this is, you can imagine, this is just taking dropping numbers from 1 to 3, well, from 0 to 2, and taking that, or or doing it from the reverse complement. But the one I am actually interested in right now is CRF. So CRF will take an amino acid sequence and it will extract all the protein strings that this sequence can encode. And I chose a little bit of different encoding for the proteins. So some sequences encode stop codons, and those are the places where we need to stop decoding a protein string. And I marked those with $signs, which is a convention that I also used in my code. The more precise problem statement is that we have to return substrings of any of the reading frames, which start with an M amino acid and end just before the following $sign. And in the first example, we can see that the first $sign will stop the sequences starting at this M and this M, but the last M does not have a $sign to its right, so it will not start any protein sequence. Whereas in the second sequence, we have a $sign at the end, and so we will also have this protein sequence MB. So how do we do this? I started thinking about the solution from the standpoint of someone who mainly thinks in types and in type systems. So I immediately thought that we would need to apply some function that splits a sequence, and then apply other functions to all of the splits which come from any of the inputs that were provided originally. So what we actually need is a flat map modifier. So this, for anyone who cannot read Haskell types, this A arrow bracket B is a function of something of type A to a sequence of things of type B. Then this type signature basically says that if we have one of these, and we have a sequence of things of type A, then applying the derived function will give us something of type B, sequence of B. Right. So in APL, the implementation of this is quite simple. We have the modifier takes the left function argument alpha alpha, applies it to each element of omega, and then catenate reduces the result. And so we can see that if we apply it with the constant function of the list ABC to a list of 5 elements, then we will get ABC repeated 5 times. Right, so how do we do this? We will need to take the starting sequence, and we would like to write a function that takes a sequence of amino acids and gives a sequence of sequences of amino acid, so that we can later apply our flat map modifier and turn it into a function from sequence of amino acids to sequence of amino acids, which will be our final type signature. Right, so the way we do this is that we partition by $sign, and then we conditionally can choose to drop the last partition if the string didn't end in a $sign, right? So I apologize. Yeah, we can see that in the first case, this XX subsequence always also presents in the output, but if we drop the last element conditionally, then it will not appear, which is what we want. So moving on, now we have a list of the splits between $signs, discarding the last one, and we want all the suffixes of subsequences of these which start with an M amino acid. So the first thing I did was I used the partition enclose primitive to give me all the subsequences that start with an M and end just before the next M. This is not actually what we want, because we would like the first sequence to start at the first M, but end at the last B, right? So what we can do is that we apply to this concatenation scan from the back. So this is a fancy incantation. It's catenate flip scan in reverse, which will give us magically the suffixes of the list, which is actually our final solution. So we can put it all together in a function of list of amino acid to list of amino acid. And so our solution will just apply the first step we chose to the input, and then apply to that the second step, each with the flapped map modifier to keep the list flat. And then there is a little unique at the end to make sure that we only return each sequence once. Right, so this was the first solution, but then I thought, well, this is not really array-like, right? We're manipulating a lot of little lists, and I would like to be working on all of the data at once, right? And so I thought about the second solution, which is the one I'm not sure if I ever submitted, but basically it is based on a different kind of approach. So we will take all of the inputs and collapse it together, inserting $signs between all of the sequences. And this introduces some degenerate solutions because, for example, this sequence $MB should not contain any amino acid sequences because the M is not followed by any $signs. However, in the concatenated string, it is followed by these $signs, which means that we will have to discard this solution somehow. And the way I handle this situation is that I also record the positions of the inserted $signs in the sequence, which is achieved through this plus scan of the lengths of the sequences. Right, and I've color-coded the numbers to the $signs so that you can see the correspondence. Right, so now we have to find the actual beginnings and endings of all of the subsequences. The way we do this is that we first find all of the M's and all of the $. And we perform iota underscore to find the positions of the matches. Then we can decide to, what we get out of this is these positions 3, 6, and 8 correspond to all of the M's, and the other positions 2, 5, 7, 10, and 11 correspond to the positions of the $signs. And you can see that we also have the spurious $signs inserted as well. Right, so now what we will do is that we apply this binary search with a dyadic iota underscore to find for each of the starts which is the ending sign that terminates the corresponding sequence. Right, and you can see that, for example, for the M at position 3, the corresponding $sign is at position 2 in the list. So it is actually the fifth, the $sign at position 5 in the input, which we inserted manually. So we will have to remove the solution later. And indexing, we get this matrix. 3, 6, and 8 are the starts, and 5, 7, and 10 are the ends. What we will now do is that we will apply a reduction with this function that where we will apply a compress with this mask, which is contains a 1 where the second component does not appear in the list of positions of inserted $signs, and a 0 otherwise. Right. So this will remove the first column of the matrix because the closing $sign was inserted manually. And then there is some arithmetic to get a list of beginnings and a list of ends to the sequences, and we can put this all together in the final solution. So at the end, we will have just a unique of dropping the beginning index, of taking the end index of every sequence, right? And this is the final solution that I ended up with, and I think it's kind of interesting that I found two completely different solutions to the same problem. Right, so now I would like to talk about the second problem that I will present, which is time for a change. The description of this was a little bit longer. So we would like a function that given a scalar right argument and a list left argument will give us all of the possible combinations of elements in the left argument that sum up to the right argument. So I summarize the constraints here below. So we want a non-negative integer matrix R with unique rows maximizing the length under the constraint that the matrix product of this with the left argument is composed of all entries equal to omega. Right, so how do we implement this? We do some recursion. And recursion is can get a little bit dangerous when you talk about combinatorial problems. So I thought it might be nice to try some pruning. And one factor in mathematics that is quite well known is that if you have a list of values a1 to an, which are integers, then the GCD of these values can divide an integer number omega if and only if there is a choice of the coefficients b1 to bn, beta 1 to beta n, as integers, such that the linear combination of alpha I times beta I equals omega. Right, so this is the factor we will exploit. Of course, we have a z here, and we actually want positive integer solutions. So it is not actually trivial why this kind of pruning works. And in fact, it doesn't. It can accept some, it can fail to prune early enough in some cases, but all of the cases are actually handled when the tally of alpha equals 1. So the worst that can happen is that we recurse too deep, and then we don't find a solution. Right, so the base case is trivial. We just table the omega divided by the first element of alpha, which is guaranteed to be an integer because we passed the first guard. So what do we do in the inductive step? First of all, we would like to find how many times can we remove the biggest coin we have from the result. And so we will just divide omega by the last element of alpha, take the floor, take the iota of this number, and we would also like to be able to subtract 0 of the biggest kind of coin. So for alpha equals alpha matching 1 to 3 and omega matching 7, we will get 0, 1, and 2. So this is the possible amounts of coins of denomination 3 that we can subtract from the value 7. Now we solve the sub-problems by recursion. So we will be able to tell that the amounts left over from this subtraction will be omega subtracting alpha times, well, the last element of alpha times the amounts of coins that we decided we would be subtracting. And we will recurse dropping the last element of alpha. So by inductive hypothesis, this will give us, for each recursion, the desired solution. And now all we have to do is that we will concatenate to the right of the matrix the amount of coins that we took away from the total. So in the first case, we took away 0 coins. In the second case, we took away 1. And in the third case, we took away 2 coins. Right, so we can now give our final solution. The formatting is a little bit different from the one that I actually submitted, but we will just do this catenate reduction of our matrix, which is actually the final result. So I have, how much time do I have? Oh yeah, so I think we have a bit of time to do a little bit of live coding, I guess, because I actually found a different solution, a little bit of an improvement over this one, which uses a technique in dynamic programming. So I'm not only going to discuss it on my blog, but also right here. So, right, so we have, this is our solution. I will be also showing you a little bit of my workflow in working with APL, which I think is quite different from some of the ones which you are familiar with. In the left window, I have my text editor. And in the right window, I have just a terminal, which I am using to watch the result of the APL script that I'm editing, right? So anytime I save every time I save my file, I will get the result on the right. And so what we need to do is, well, since this is a recursive function, I decided to keep bootstrapping implementation to handle the recursive calls. So I can just show you the inductive step. What we will do is that we will try to share the subproblems from the different recursive calls, so that we can solve them each only once instead of solving the same one different time, a higher amount of times. Right. So the first part is going to be exactly the same as the other solution. So we will take the last element of A, and I will show you. Then we will assign this to B so that we can reuse it later, and divide omega, which I will simulate with W. Yes, and I will take the floor of this amount. This will give us 2 and 3, because we are actually solving. We are dealing with a slightly modified version of the problem, in which we solve an array for an array right argument, and we give back an array of matrices, right? And this will allow us to handle the inductive step a little bit better. So we will get a result of 2 for the 7 and a result of 3 for the 10. We can then perform iota each on this. And I will raise it. And we get 1, 2, 1, 2, 3. We will then catenate a 0 to each of these, just as in the initial solution. And these are all of the amounts to take away from each of omega. So our subproblems, which I will mark as P, will be omega minus A times each of these, which I will mark as I. And I will get a length error because I... oh, yeah, because I called this B. Yeah, the last element is B. Right, so these are all of the sub-problems that we would like to solve. And as we can see, there are some duplicates. So the next thing I will do is I will save some unique problems, which will be the unique of the all of the elements contained in the nested vector. And so these are the unique problems that we will solve. We will solve this by inductive hypothesis. So we will call the we will now call the makeChange function to simulate a recursive call. So this will be -1 drop of A, makeChange each of up. And these are all the solutions to the sub-problems that I found. Right. And I will call these unique solutions. And might be smart to introduce some blank lines so that we can separate the results better. Right, so the next stage will be to match the found unique solutions to the problems that generated them. And so what I will do is I will write a little defun. I will take my problems and my and the amount of times that the last element was taken from each problem, and I will use those to pick a unique solution where the problem matches the unique problem, right? And this will be an each. So if we do this, I will get an index error because right, so, oh yeah, because the problem should be alpha, and no, this should work, yeah. Right, so now we're finding all of the unique solutions in our vectors. We will also concatenate omega at the end. So we will get, let me reduce the size a little bit so it will fit, right? And so we will have unique solutions to all of the sub-problems. And then we will just apply our disclose of table reduction. Right, and these are the solutions. If we package these all up in a different, it would not be correct because we are actually returning an array all of the time due to the way each works at line 1. So the thing we will do is that we will assign this to R, and then what we will actually return is R disclosed to the power of 0 matching the rank of omega. Right, so we will need to disclose if omega was a scalar to begin with, so that the problem is compatible with the problem statement at the beginning. And I will get rid of the output on the first lines so that we only get, oh, I'm missing a right tag, yes. And this will be the final solution that we can then package into a diffun. So thank you very much. I think I actually have some last considerations, so I'll just get back to the slides. Yeah, so what I learned doing this is that APL is actually not very opinionated as a programming language, which I thought was really strange because it looks like something that would force you to take on the array paradigm. But I was actually able to map my way of thinking with with iterators in Haskell or Rust or other kinds of languages to the language. So you can actually directly translate code from other languages to APL, and it doesn't look too bad, right? And yeah, functional patterns apply with, especially lately with defense and such. But of course, all of this gets better if you try to think about array solutions to your problems. And so array programming has really been there all along. In all of the languages that I learned beforehand, it was possible to apply some things that I learned from APL. For example, with MATLAB, C++, and C mostly. And so one last thing that I would like to say is that APL really is a language that changes the way you think. And I think that's very valuable. There might be some quote that you can make reference to. Yeah, so thank you very much. This was my experience.